I'd like to say we're very happy to have Adam Smith give a talk today. Adam has done a lot of great work, starting with foundational work in privacy and cryptography, for which he had quite a few awards, including a Test of Time Award at the Theory of Cryptography Conference, a Test of Time Award at Eurocrypt, and a Gödel Prize in 2017. So that's we're very happy to have our seasons at the Foundations of Data Science seminar conclude with this talk. Adam is going to tell us about relation between memorization and machine learning, and specifically when is memorization of entire examples necessary for high accuracy learning. I'm not going to take more of the time. Adam, the floor is yours.
All right, well, thank you very much. I'm very glad to be here, and I'd like to thank Clément, Venkata, and the other organizers for inviting me. So this is joint work with Gavin Brown, who's actually here in the audience. He's a PhD student at BU, as well as my colleague, Mark Bunn, and Vitaly Feldman and Kunal Talwar, who are currently at Apple. Okay, so we know that machine learning models typically have to contain a lot of information about their training data, okay? Sometimes tons of information. What we show is that this type of, that this is unavoidable, okay? We give natural settings in which the memorization of entire examples is necessary, no matter how the learning algorithm works. And even when many of these details of these examples are ultimately irrelevant to the problem at hand. So as I go through the talk, I'll explain, what I mean by these terms, but this is the general gist of where we're trying to go. Okay, so we know that machine learning models often memorize data points explicitly. For example, if I take a one nearest neighbor classifier, like that, the description of the classifier is pretty much the description of the data set. Okay, so it's going to contain in particular, like, the points in the data. And this happens even with other kinds of models. So for example, support vector machines are typically presented in their dual form, and that those support by support vectors, and those vectors are themselves points from the data set that are accessible explicitly to the analyst. But memorization often happens in more surprising ways, and often as an unintended side effect of learning. So for example, there was this paper that got a lot of attention by Carlini, Liu, Erlingson, Kos, and Song in 2019 called The Secret Terror, showing how natural language models often will memorize exact sequences from their input, even when it's sort of clear to someone looking at this that these examples that are being memorized are kind of irrelevant to general language understanding. And this was, celebrated in this fun XKCD cartoon about how, some group of revolutionaries gets caught by like smart compose. Okay, so memorization of a different type has received a lot more of attention, and the kind that has received a lot more attention is what's often called overfitting or interpolation to the data. So, classical machine learning theory tells us that we shouldn't try to overfit to the data. We should try to find models that are as parsimonious as possible and give us an okay approximation. But we also know with current techniques, the kinds of techniques that people are using largely these days, it's often beneficial to train, say, neural network models well past the point where they fit the data perfectly in terms of they will perfectly reproduce the label of every single example in the data set. And my collaborator, Vitaly Feldman, had this paper earlier this year showing that this type of memorization of training labels is often necessary, again, no matter how the learning algorithm works. And so one can think of the result that I'm discussing as, or the results that I'll discuss, as a generalization of that tasking, not only when do you need to memorize training labels, but when do you need to memorize sort of entire data examples, and what might that mean? Okay, so here's, let me try to walk you through the basic result. I'll give you an informal version and then a slightly more precise version. Here's our basic setup. We've got data drawn from some distribution. So the data set consists of n rows drawn IID, and you might think of drawn IID from some distribution P, and we'll think of these rows as each being a bit vector of length D, we'll call it. Okay, and a good setting to have in mind is that the setting where the dimension of the problem is much bigger than n, although that's not the only setting in which our results apply. So then this data set is handed to a learning algorithm. It generates a classifier, and then the classifier is run on some fresh sample from the same population, the same distribution, and then it generates, a candidate label for this example, which is compared to the real label to determine if it's correct or not. And typical measure of error is the misclassification rate. So this is, if I hand the learning algorithm a data set and I take a fresh sample from the same distribution, what's the probability that the classifier will generate the correct label? Okay, so roughly the question we're asking is, what does this classifier M tell us about the data set X? What kinds of information can it or must it contain about X? Okay, and informally, the main result is that there are natural problems for which, for every learning algorithm that gets sufficiently close to optimal error on the problem, the mutual information between the classifier and the data set has to be very high. So, how much information could the classifier possibly contain about the data? Well, about n times d bits, because that's how much information there is in the data. And what we show are settings where you get within a constant factor of that bound. And we can even say something stronger, but I'll get to that in a couple of slides. Okay, so first, in order to make this result formal, we need to kind of specify a bit more to what's going on. And the reason is I need to tell you where this distribution P that's generating the data is coming from. Okay, because if the distribution P that's generating the data, the labeled examples, is fixed, then there's a learning algorithm that can just ignore P and generate a good, ignore the data, and just generate a good model based on its knowledge of the distribution. Okay, so in order to say something interesting, we're going to need to talk about the setup, add one more layer to the setup. And specifically, we're going to say that a learning problem is like a meta distribution. So it's a distribution on instances, and each instance is a distribution on labeled examples.
Adam, there's a question asking whether optimal here is in terms of generalization error.
I will get there momentarily. Yes, is the short answer. So what is a problem? A learning problem for us in this talk is it's a meta distribution from which the distribution, the population is sampled, and a population generates labeled examples. A population is a distribution on labeled examples. So the theorem is there's a natural problem such that for every learning algorithm with sufficiently high error, the mutual information is high. Okay, and so let me explain what sufficiently high means. So here, the error is now just based on it is taken on average over populations generated according to this meta distribution. And then once we've fixed P, we're going to look at the expectation over data sets of the generalization error. Okay, and there's the randomness is also taken over any random choices made by the learner and the classifier. But if you prefer to think of those as deterministic for the talk, that's fine. But it makes sense even for randomized tasks, randomized algorithms. Okay, so what's going on now? Sorry, that's probably a little hard to read. Let me erase it.
Well, Adam, we have another question in the chat. So what is the difference between memorization and overfitting? Is memorization required for overfitting?
We're gonna let me finish walking through the slide, and then I'll address that question.
Sure.
Okay, so there's a natural meta problem such that if I've got an algorithm that does well on average for this number of samples and this meta distribution, so that's what this optimal means is it's expected generalization error on average over populations drawn from Q and data sets drawn from that population and samples tested on a fresh sample from the same population. If your error is close to optimal, then you need to contain the model contains a lot of information about the data set. And this is true even conditioned on a complete description of the distribution, the population. Okay, so it's kind of not trivial to prove, but sort of clear that the model has to contain information about something. And in particular, it had better contain information about the population P, because otherwise it's not going to be a reasonable classifier, right? But this is a stronger statement than that. This is saying that the model has to contain lots of information about the data that is really specific to the data. So specific to the data means it's entropy that's there even after you condition on a complete description of the problem. So again, here an instance of the problem is just an instance is a distribution on labeled examples. This instance is chosen randomly from the meta distribution. And this optimal error is the best possible average error for a learner given, for a learner that does not know P but is given n samples. So it knows Q, it doesn't directly know P. The only way it learns about P is via the data it has. Okay. So now I'm happy to try to answer some questions. One question was whether or not this is about generalization error. The answer is yes. Another question actually now maybe I'll need help because I see there are more questions in the chat. All right, the first question was about memorization versus overfitting. So actually, we'll talk about that, but in some sense, one of the things we'll show for these problems is that in order to do well on the problem, you must in particular overfit. But more than that, you have to encode lots of information that's like a lot more than just the labels. So the labels here would be information on the order of n or maybe n log n, depending on exactly what the labeling problem is. But the labels there's no dependency. If I were just memorizing labels, there'd be no dependency on D or a very mild dependency on the dimension. So here what we're saying is actually you encode tons of information about the data, like way more than is just in the labels. So it's not directly about overfitting, although along the way we're going to show that the algorithms have to overfit. I doubt I'll get to that level of granularity in the proofs, honestly. Sasha is asking is this with high probability of the choice of P or an expectation over the choice of P? This is expectation over so the error model here is I'm asking for on average error over the choice of P. And then the mutual information measure this is the standard notion of conditional mutual information. So this is the mutual information between X and M conditioned on a particular problem, and then we're going to average over problems selected from the meta distribution Q. Okay, that's what conditional mutual information, that's how it's defined. So it's on average over the family. Okay, so Somesh is asking, how come the complexity of the hypothesis space doesn't appear in the theorem? I guess it implicitly does just via the, so I haven't sort of told you what the problems are, but they're going to be more complex depending on the dimension. So the dimension of the data affects the types of problems we'll get. And I will, like, in a few slides, give you like exact problems that we're talking about, but I try to get there one step at a time. So yeah.
I have another question regarding the error. So like, yes, if the error is like smaller than the optimal plus some small offset, why should I think of opt-n here? Is like the optimal error actually very big or very close to zero?
Yeah, it's well, it can depend on the problem, but I think of the optimal error itself might be 5% or something like that, like a small constant in most of the sets. Yeah, in most of the things we look at, it's a small constant. It's probably the right way to think of it.
Thanks.
Okay, so this is the first version. This is version 1 of the main result. We can actually say a little more, which is we can actually talk about like specific examples in the input. So a strengthening of the statement, which we can prove for some setups and not for others, is that there's a natural problem for which every data set has a special subset of inputs. Okay, so we'll call that S of X. So these are like the special labeled examples. Such that on one hand, there's a lot of information in these labeled examples. So the entropy of the examples conditioned on the population is high. And any learning algorithm that approximates the that gets close to optimal error, again on average of the population, has mutual information that is essentially there's mutual information between this subset and the model that is essentially the entire subset. So it's got like all the information about S times some multiplier that's close to 1, and that multiplier goes to 1 as the error goes to 0. So, but for like small, if epsilon is a small constant, then f of epsilon is some other small constant that's not quite as small. Okay, and I'll give you at least one version where I spell out what f is, but it's some complicated formula normally. Okay, so what the meta interpretation here is that there's in the data there's a lot of information that's not really about the problem, the instance. It's like extra information. But a successful learner can't tell what information is like really useful and what information is just noise. And so a successful learner has to memorize the noise along with the signal. Furthermore, for the examples we come up with, for at least some of them, they have the feature that if the learner happened to know a complete description of P, it could come up with a really good hypothesis, a really good model, which is like quite short. In fact, its complexity is on the order of n, or maybe n log d or something like that. It depends exactly on the problem. But like roughly speaking, there's a way in these problems for a learner that knows the complete distribution to kind of project things into a smaller dimensional space and memorize, learn only some smaller dimensional thing, and remember only this kind of concise summary. So what that means is like another version of that is to say if we were to fix this n, so fix the problem and then let the amount of data go to infinity. So if I were just give you tons and tons of samples from the same distribution, eventually you would learn the generating distribution or something close to that. And you would be able to come up with a much compressed model, okay, vastly compressed model. in fact, the examples that we have, I guess you need about like, not n, but like n log n examples. So just like a little more data, and you can learn a pretty good picture of the distribution and a small classifier. But if you only get n examples, then and you want to do as well as you possibly could with like that number of examples. So if you're trying to milk everything you can get out of CFAR 100, then you're going to have to memorize lots of stuff that's not really about the problem. Okay, so that's the main theorem. And now what I'd like to do is tell you a little more about like the specific problems and how they come up. And then, to the extent I have time, I'll try to talk about like how we prove these things and what are the what are the kind of technical issues that come up. So question from Jeremiah Blocky: are we assuming that the rows in X are incompressible? That is, can we say anything if h of X is little o of nd? I guess we set it up so that the rows of X are not compressible until you know a lot more about the problem. I guess you could try to come up with a slightly more general version where we would, like actually this statement here is sort of just is a relative statement. It just says, how much information is in these special examples. That's how much you remember. And then the question is, can we get this number to be small? And I guess you could, but I feel it's like a less interesting example. But yeah, I suppose we could. Okay, so let me tell you a little bit about the kinds of problems that come up, because I think it'll help understand. Once I've walked you through the examples, the whole thing will seem a lot more natural.
Adam, before we move forward, so there was another question which asked, like, do you have a sense of the cardinality of S?
Oh yeah, I guess it. Yeah, I don't have it on the slide, but this this means that the fact that the entropy is like n times d implies in particular that but like we'll set it up the other way. We'll first ensure that the size of S is big, and then ensure that that has a lot of entropy. So yeah, it's like a constant fraction of the data.
Okay.
Great. Okay, so all right, so the problems we're going to consider, we consider a few different ones, but they have the same high-level structure, which is that each one is going to be a mixture of many clusters, many little subpopulations, a mixture of distributions and subpopulations. And the way we're going to imagine specifying this like meta distribution is, first there's going to be some distribution on mixture coefficients. Okay. Wei-Jie, I'll get to your question in a second. So first, you can think of this as a distribution on mixture coefficients. So it turns out that, like, for the purpose of this talk, you can just imagine that mixture, the coefficients are always uniform over n subpopulations, where n happens to be the number of data points, or order of n subpopulations. But we consider other setups that are not just uniform mixture weights. In particular, these kind of long tail type distributions. All right, so and then you've got this distribution on subpopulation instances. So for each subpopulation, I've got this like little tiny meta distribution that, from which I pick a problem for that subpopulation. Okay, so I've got this sort of hierarchical structure. So within each cluster, within each subcluster, or I'll use equivalently to the word subpopulation, we've got a different distribution on labeled examples, and that's selected independently from some little meta distribution, little q. And we consider two plus types of problems. I'll tell you about two types of problems.
So
yep.
There's another question in the chat asking whether S can be thought of as the support points in SVM, or whether where the margin is saturated.
Right. Yeah, that's a good question. So these are not, I don't know, whether or not they can, but the examples aren't naturally like set up as like the right classifier isn't naturally set up as a half plane, half space, even in some kernel space, I think. I don't know. I guess I haven't tried to think of it that way, but we certainly weren't thinking of the like natural way to approach these problems as say fitting a half plane or anything like that. So I'm not sure exactly how to answer that question. And maybe I should just mention that this sort of at the level, this idea of sort of looking at how these mixtures with lots of small subpopulations was also used in Feldman's previous work, I should mention. Okay, so let me tell you like what these subproblems look like. So, so one is what we'll call hypercube clustering. So here, within each subpopulation, the distribution is specified by a set of special indices. So it's a distribution, on bit strings. It's specified by a set of special indices, and the positions of these indices are fixed in the subpopulation, but they are everything else is random. So the description of the subpopulation, it consists of the set of indices that matter and their values. Okay, so at the meta level, those things are uniform, but they're fixed for each subpopulation. There's a fixed value. And then what a fresh example from this population consists of generating the remaining unspecified entries uniformly at random and appending a label, which is just the name of the cluster, the name of the subpopulation. Okay, so basically, you could say like these are images of cats, whatever, and what makes them images of cats are the following special positions. Okay, and we call it hypercube clustering because it's once you describe the subpopulation, you're sampling uniformly from a hypercube. Okay, another thing we consider, the other kind of class of problems we look at are next bit prediction problems. So here, the subpopulation is specified by a core underlying string. We'll call it CJ of bits, okay? And some noise parameter, delta. And now to generate a labeled example from this subpopulation, what I do is first I tell you J, that's part of the description of the example, it's not the label. And then I sample a length L, which is not the whole string. And what I do is then I feed the corresponding prefix of C through a binary symmetric channel. So this just means each bit gets flipped with probability delta. And so what I get is sort of mostly the same thing as in C, but there's some delta fraction of positions that are flipped. And then the label is similarly a noisy version of the L plus first position of C. Okay, so the right way to think of it is there's some underlying thing that I want to predict. I want to be able to predict from. So my problem consists of given a prefix, I want to be able to predict the next word in the sentence, if you will, but in this case, it's just a bit. Okay, so this problem was chosen to sort of have the same flavor as the kind of next word prediction problems that something like Smart Compose is trying to solve. It's just a very stylized version of that, a very simple stylized version of that. And then the hypercube clustering problem is meant to be just like a classic geometric clustering problem. You can think of it as some, multi-class, just a sort of a classic multi-class classification problem. So to come back to Weije's question about SVMs, maybe there's some way to embed these things in a higher dimensional space that makes them look like makes the optimal classifier look linear. I don't know, but a priori, that's not how their flavor. Okay, so basically, so these are the two kinds of problems we consider. Also, we also consider results on threshold classification within each subpopulation. It turns out that, it's actually thresholds can be embedded in this next bit prediction problem, and if you do it right. And so those are basically just corollaries of what we have to say about next bit prediction. So I'm just going to talk about those two to the extent I have time. All right, so what's going on? Let me try to give you some intuition of why memorization shows up. So the idea is that, like, for example, if my mixture distribution is uniform over n clusters, and I get n samples, then actually I expect to have a constant fraction of my data lie all alone in for a constant fraction of my data points. They will lie alone, be the only representative of their subpopulation in the data set. Okay, so we'll call these things singletons. Right? So a singleton is a labeled example which is the only training point from its subpopulation. And as such, it has a lot of weight on its shoulders to kind of represent the subpopulation, if you will. And so what we prove is that a learning algorithm has to memorize these singletons. So each one is a d-bit string or order of d-bits. It has to basically memorize these singletons to perform well on test points from that cluster. And roughly speaking, if I want to do well on the population overall, these clusters from which I got the singletons, they represent a constant fraction of the overall population. So if I do well on the overall population, I have to in particular do well on most of the clusters from which I saw singletons. Okay, and the way we do this is by giving, well, there's sort of two different flavors of things we do. One is we provide lower bounds for sort of one-shot learning, like what happens when you just get one sample from a subpopulation. So that's what's going on in the next bit prediction problem, and that's the thing we analyze. For the clustering, for the hypercube clustering, it's a bit more complicated, but the problem we end up looking at is some kind of nearest neighbor problem and I'll explain why that shows up, or I'll try to anyway. Okay, so I see there are a bunch of questions, so I will see if I can get through some of them. Oh, okay, no, most of these are old, but a new one. How about algorithms that identify such singletons as noise? So here's the problem, is that these singletons, they're not noise, or they're not all noise. So the singletons, they represent populations that themselves are like a constant fraction of the probability mass for the problem overall. Okay, so for example, if I've got some image classification problem or a text classification problem, there are certain classes from which I'll see lots of examples. I've got lots of cat pictures, fine. But then there are some classes that will be very poorly represented. They might have just one or a couple of examples. Like I might really only have one photograph of a wolf where the wolf is not on a snowy background. And so what do I do with that example, right? So I can ignore it, but in this particular case, I could ignore that one thing and that would be okay. But if I ignore all of the things like that, all of the things that are like lone examples of their type, then I'm really shooting myself in the foot, and I will end up getting a strongly suboptimal classifier. So if I'm competing on Kaggle and I really want to get to the top of the leaderboard, then I need to memorize these singletons, and as we show, I need to memorize like all this stuff about the singletons that's actually turns out, if I had more data, I would understand was not relevant.
Could I ask a follow-up question?
Yeah.
it could be that like this one picture of a wolf without a snowy background is really the only picture you'll ever see. You could forget about it. So is the difficulty, is the reason you have to memorize is you can't distinguish whether is really idiosyncratic and nothing like it will ever be seen again, versus the sorts of pictures that you happen to have one example of, but if you double the size of your data set, you'd probably see more of them.
Yeah, that's a great question. So actually,
memorization is required because you can't do it.
Yeah, so but both can occur, and exactly what the balance between them is depends on how these mixture coefficients are distributed. So if the mixture coefficients are always uniform, then you only get like the second type, the kind that if you saw more data, you'd get more like that. But there are other settings where the mixture coefficients are highly unbalanced. And then when you see a singleton, you actually don't know if it's like from a subpopulation that is important, and if you had more data, you'd see more of, or from a subpopulation that really, actually never will never occur again. Wolves that were photographed, with Dungeons and Dragons game in the background, so there was also like a dragon head next to the wolf, right? Like, I don't know, whatever. Okay, so the part of the issue that sort of depends on how you set up the mixture coefficients. I'm not going to talk about that in my talk. I've only got 10 minutes left, but I will. But it comes up in the paper, and we discuss like for different kind of types of mixture coefficients, what kinds of stuff happens. Okay, so
there was another question.
Oh, great.
Does this? Yeah.
Someone asks, does this mean to perform well on underrepresented groups, we'd need to memorize them? And if we do, then does this mean underrepresented groups would get less privacy? Yes, that's exactly what it means, unfortunately. So if you think of these subpopulations as like people, and people from subpopulations within the bigger population, then it means that in particular, the subpopulations that are kind of light. So if you've got subpopulations that are like not very big, but big enough that it's important to remember them, or maybe perhaps you can't tell if it's important to remember them, then optimal strategy is to memorize their data almost completely. Whereas for the people from the subpopulations that are better represented in the data set, you can often come up with either a much compressed representation or one that sort of ignores them and ignores individuals and is kind of just reflects the underlying distribution and not particular samples. Yeah, so that is I don't think ours is the first paper to observe that, but this is a kind of a crisp setting where providing privacy to small subpopulations comes at an enormous, like a really big cost in terms of your performance. That was one of the things I was going to mention later, but I'll get there. Okay, so I should, before I go any further, I should talk about related work, because of course this, we don't exist in a vacuum. As always, we stand on others' shoulders. So as I mentioned, this work of Vitali's earlier on label memorization, that was definitely an impetus to this current project. There's a small line of papers relatively recent on learners that leak little information about their data. So these papers, came at this problem from a different motivation, but actually gave results that have a similar flavor, but are quantitatively and, well, I guess qualitatively much weaker. So in these results, the bounds if you try to transform them into our setting, which they're not like phrased this way, but if you do, you get some bounds that are something like n times log d. So it's a much weaker type of statement about how much is memorized. That said, they're not strictly comparable. So like you know, I don't have time to go into the differences, but like, you know, definitely it's not that we subsume completely those works, but it's another point on the Pareto curve, if you will. And one thing that we got a lot of inspiration from is a line of work on representation complexity. So this is started from this work of Bemel, Nassim, and Stemmer, received some further investigation, notably by Feldman and Shao. And they provide a lower, the right way to think of these lower bounds is they lower bound, they show that the mutual information between the model and the problem has to be big. So they give like a measure of complexity of a learning problem, a pack learning problem, which basically boils down to showing that the model has to be big. It has to have a lot of bits in it. But those arguments don't show that the information has to be of the type that I'm talking about. Like, in fact, the way you get the lower bounds of that type, from the representation complexity work is by showing that the model contains lots of information about the underlying distribution. There's another kind of line of work that on time-space trade-offs for learning. So these are lower bounds for a streaming style computation model. For example, Ron Raz, you know, showed in a paper that got lots of attention that learning parity over d-bit strings requires either like order of d squared memory to as you're passing through the data set, or an exponential number of samples. So it's a beautiful result. Our results aren't really about the same setting. Our results are about the size or information content of the final model, which is different. But they do, you know, I don't know, we haven't really worked it out. We think that there might be some connection, some implication for these streaming style settings, maybe, but like it would be much weaker. It wouldn't really reflect the kind of strong exponential versus polynomial trade-off that you get with these parity learning. The results, on the other hand, are problems I would argue are much closer to the kinds of things people try to solve in real life with learning. So, yeah. Okay. There's a lot more work on various connections between information theory and learning. I'm not going to go into all of it, but I wanted to kind of situate our work within this body of work and just emphasize that really there are a lot of interesting connections there. Okay, so what are some of the implications of our results? Well, you know, what I say on the slide here is that these models that are sometimes called giant models, like GPT-3, which got a lot of attention recently, it's a language learning model. These types of like really huge models might be unavoidable if we want to get as much as we possibly can out of the data sets we collect. And furthermore, not only do they have to be big, so that in some sense is the representation complexity side of things, but they have to encode information about lots of information about individual examples. And I would guess there's lots of like interesting experimental work to be done trying to figure out what things like GPT-3 really encode. These results also provide like yet another way in which privacy is difficult. So in particular, if you've got an algorithm that's differentially private, you can argue that it's the mutual information between the mutual information between the data and the model conditioned on the problem is small. Okay, so actually, the mutual information between the model and the problem might be high, but the mutual information between the data and the model conditioned on the problem is, you know, it's much smaller than n times d. Okay, so typically this would be like little o of 1, and this thing might be order of n, but much smaller than n times d. Okay, so differentially private algorithms can't hope to, in particular, compete with optimal learners for this kind of problem. I'd argue this is a somewhat novel aspect to the privacy challenges we see. It's sort of reflecting a different type of problem. Okay, so I've just got a couple of minutes left. I'll just give you a flavor of what's going on in, like at a technical level in these statements. So the main idea is to kind of reduce things to some kind of communication game, and to look at the information complexity, the one-way information complexity of some game between two players, Alice and Bob, where Alice's job is to come up with a learning model, and she's going to send it to Bob, and then Bob will try to classify some fresh example given that model. And then we'll argue that Alice has to put a lot of stuff into that one message in order for Bob to succeed. So I'll let's see if I can say something quickly about it. So for example, for next symbol prediction, what's going on is that here's Alice over here. So she gets like, so what we show, I don't have the reduction, but what we show is that like if she's just given one, we look at just what happens with one subpopulation. She only gets one example from that subpopulation. What we argue is that the the model she produces has to contain a lot of information about the message, and I guess this is not. There's the conditional statement is missing. Oh no, wait, sorry. This is actually, this might be without conditioning. Okay, so what we argue is that the mutual information between her message and between her one data point and what she sends to Bob has to be very high. The d/2 is like the actual entropy of her one data point. Okay, and then it's multiplied by some number that goes to 1 as she gets better and better at her job. And then we also show that necessary, and roughly speaking, there's a second step to show that the part of that is actually about P is smallish, smaller anyway, little o of the quantity above, and so you can argue that she has to encode a lot of information that's actually about the problem. For clustering, what goes on is arguably, I think, a little more interesting at a technical level. So there to get the lower bound we want, the kinds of lower bounds we want, we have to look at like a block of k singletons. So think of k x1 through xk as all of the singletons in the data set. So Alice gets like k samples. So that's d times k bits, actually a little more because it comes with labels, but ignore those for a second. And we just look at, like, suppose we tell Alice, hey, all you have to do is do well on the singletons. You can just ignore everything else. Okay. And we guarantee that Bob's labeled example, unlabeled example, his test example, is going to come from one of those k subpopulations. So we look at that problem. And it turns out that if you kind of write down what that problem is and stare at it for a little bit, you can realize that you can strip away a lot of the clustering business, and you get to actually a pretty simple problem where Alice's data is just a bunch of uniformly random strings. And what Bob gets is a new data point that's close to one of them. So, Alice gets these k strings, and what Bob gets is like a corrupted version of one of them. That's Bob's input. Okay, and how corrupted? Well, it depends on like how you set up the problem, but if you choose the set of fixed positions to have size rho times d, then the corruption probability is about 1 minus rho over 2. Well, exactly 1 minus rho over 2. And so this is sort of a corruption probability that's relatively close to 1/2 in this regime. And so what you can argue here is that, well, so that's like the main observation, is that Alice and Bob are really solving some distributional version of a nearest neighbors problem. Okay, Alice gets k points, Bob gets something that's close-ish to one of them and has to figure out which one he got. Okay, so if Alice just sends all of her data over, they can solve this pretty well. It's the parameters are set up so that they can solve this with probability, some high constant probability, let's say 95%. What one can argue is, so what we prove is that Alice's message to Bob has to be, if they do well at this game, has to be on the order of k times d. Okay, and that is enough. So that's what we prove using what's called a strong data processing inequality. I'm not going to go through the proof. What we conjecture is that actually her message needs to contain k times d times 1 minus little o 1 bits of information, where little o 1 here is some small function of epsilon, the degree to which they're failing to solve the problem optimally. And if that conjecture is true, then we can actually get this sort of the stronger type of statement I made earlier in the talk for this clustering problem. So currently, we can only prove the stronger statement for next bit prediction and thresholds. For the clustering problem, we can prove only something a bit weaker. But we conjecture the stronger statement to be true, and we can prove like special cases of related problems that I'm not going to describe, but are in the paper. But the problem we really want to solve at this point is still open. And what the thing we figured out is that at least the current toolbox of communication complexity doesn't solve the problem for us. We need some new idea. Yeah, so Somesh is asking how much do they compress by constant factor? Yeah, so what we can argue is that Alice can't compress her input by more than a constant factor. So in fact, what we get is something like 1/2 log 2. So this is what we can prove. So 1/2 log 2 is like some constant that's not 1. No, it's less than 1. So we can prove you can't compress more than that. But I don't think we can get more than that. I see. Now I'm reading the comments. Somesh was asking, okay, so there are compressed versions of GPT-3, which are almost as accurate as the original one. The compressed versions are the ones which are used mostly. Any thoughts on what happens, which information is lost during pruning and compressing? I'm not going to offer any thoughts on GPT-3. I don't know enough about its structure, honestly. If I had to hazard a guess, it's you're losing information, to some extent, information about subpopulations, and then within it's like how finely granularly do you break down the things that you might have, the tasks that you might have to consider, and also like how much do you do things like dimension reduction and stuff, that other ways to save on space without sacrificing too much accuracy. I don't know enough about GPT-3 to offer anything really concrete. I see. Oh, there's a nice, okay, someone is sending a link to a paper on compression and how it affects membership inference. Yeah, that's interesting. So this paper, one thing I haven't talked about is that the kinds of statements we're making are not really about membership inference or actual reconstruction of explicit examples. Okay, so we're at this level, what we can prove are mutual information lower bounds. We have a sense that there is something to be said about actual explicit reconstruction and sort of concrete attacks. But at this point, we're not sure what those statements what kinds of statements would be provable or true. What is clear is all the strategies we can think of to solve these problems accurately just basically reveal stuff in the clear to first approximation. And so Like we certainly don't know of any like non-trivial ways to not just like print out the data. But that doesn't mean it's, there isn't something better. Okay, so I'll I'll just sort of leave some conclusions on the slide. Memorization is sometimes necessary. Proofs, no matter how the algorithm works, I think that's the interesting part of the statement. The proofs we give some insight into what features of a problem lead to memorization, and they give some reasons for optimism, right? So in the problems we look at, if you've got n samples, but you're really okay with doing as well as you could do with n over 10 samples, then, with a sample of size n over 10, then you can avoid a lot of these problems. Not all. But that's like, that's kind of weak sauce, because people, if you go to a statistician and tell them, don't worry, you'll get as much utility out of this survey as if you talk to like 1/10 of the number of people and spent 1/10 of the money, they're not going to take you seriously. And so there really is a real trade-off here that we're wrangling with. Okay, question from Sasho. I guess formally the mutual information lower bounds don't immediately give lower bounds for approximate DP. They do. So I kind of said it briefly. I can go back though. If I have it on the slide, where do I have it? Here. So mutual information lower bounds do give results for approximate differential privacy. So like any epsilon delta differentially private algorithm, this is for epsilon less than 1, the way it's stated, gets me about, okay, fine, of this this upper bound. So there really is like even any reasonable variation on differential privacy will leak a small amount of information. So there is a real conflict there. Jeremiah, I want to give, okay, so, all right. Rithik is asking, so I didn't get a lot about the technical aspects of the talk, but from a social point of view, the more unique a data point is, the more necessary it is to include it for accuracy, but the more at risk of being found out by an adversary. Yeah, that's a good like high level intuition for what's going on. Namely, these data points that are somehow special in that they are the only data point or one of a very small number of data set points that's telling you about a subpopulation. It's hard to not keep a lot of information of those around without basically giving up on that subpopulation, and that could be a serious problem if you do that for lots of subpopulations. Shiva Kashiva Swanathan has clearly someone else on his keyboard, some cat or child. I've been there, I sympathize. Okay, I'm happy to take other questions or let people go. I see it's 2 o'clock, so I'll stick around, but if people need to run, by all means. Someone is asking if we considered active learning as an antidote. I don't know to what extent active learning would help us here, in as much as the issue isn't really which examples get labeled. But maybe there's something there that I don't see. I don't know. Can a possible solution be oversampling the subpopulation so it creates a sort of mask? Yes. So one thing that you could do, and if it were possible to like change your survey weights, for example, to ensure that in your data you've got lots of representatives from the subpopulations, from important subpopulations, from all of the subpopulations, let's say, then you could solve this problem reasonably well. Of course, often we're tasked with doing learning or inference from the data we have, and we don't have that much control over the process. But if you can, shift either the underlying distribution or the weights from the way your data is collected, then you might be able to alleviate a lot of these problems, at least for the examples we consider. Okay, So I'm happy to take more questions, or we can call it a day.
A quick question from me, Adam. So does the converse in some way also hold? Like if you have like a large number of samples from some population, is it possible to compress so that we can just keep one sample with us and that should be sufficient for us?
Yeah, so let me see if I have that. There is a sense in which the answer is yes. So there's like one, I mean, I don't know. I think there's probably more to say about that, but one version of that is a paper of Nahum and Yodayev that appeared this year, where again, their motivation is a little different, but like interpreted in our context, they gave a specific class of problems of like PAC style learning problems, where if I understood the implication of the result correctly, once I have enough data, there's a way to compress it to something that's basically depends only on the distribution and not anymore on the data. Okay. Yeah. In terms of PAC learning, you can think of it as sort of roughly you can converge on some kind of canonical consistent hypothesis for a problem for a given distribution for a given distribution.
Okay,
yes.
Thanks.
Mm-hmm.
So do we have any more questions?